Hi, everyone. Welcome to the second session where we're talking about this wonderful tutorial, Inference Optimization for Foundation Models on AI Accelerators. We say foundation models, we're really talking about LLMs predominantly. Um, so this was, again, an AWS tutorial presentation at the KDD conference about a month ago. Um, and they just put together such a wonderful roadmap that we're going to go through this. So very quickly, I'm going to flip through the slides. Last week, one second, yeah. So last week we talked about, hey, models are getting bigger, and this conversation that even though we've had conversations about how many millions of hours some of these foundation models were trained on, the reality is now that we have millions of people using these LLMs, there's actually more compute going towards inference than there was in the original training. So motivating, that's why this is an interesting problem to solve to optimize the inference. All right, so we're going to get a little primer on LLMs, attention, all this stuff. Not going to go through this. The most important thing to know is that in attention, you're calculating queries and keys for every token. I may use the informal term word instead of the formal term token. I tend to use them interchangeably, just for the purpose of easy understanding. So every word gets two vector embeddings when it goes into an attention layer. One is for the query, one is for the key, and basically the query gets dotted with the key for every other token position, and ultimately those are normalized into scores that sum up to 1. So the most important thing to know is that as you get a longer and longer context, you are doing more and more computation, and you need access to these numbers for every possible key. So when we are now talking about length 128,000 or 1 million, it means that token towards the very end, in fact, needs to see 100,000 or even potentially a million keys in order to calculate those scores that sum up to 1. All right, so that was the main thing that we reviewed, and then a little bit about the architecture in general, what Llama looks like, a little different from the original Vaswani paper, and then this idea that really when you're working with an LLM, you could hypothetically, if you start with a long prompt that's 10,000 characters long, you could just process them one token at a time. 10,000 tokens long is what I meant to say. You could process it one token at a time, but there's no need for you to do that. It's very inefficient. You know that the original prompt is 10,000 tokens. You can process all 10,000 of them at once. At that point, you have no choice but to do inference one token at a time. And then once you get that next token prediction, however you do it, whether you're doing zero temperature, or you're doing sampling, whatever you're doing, but once you know what the next token is, then you append that to the end and you do another inference pass. And there's really no way to sort of prevent the fact that you cannot know in advance that the answer is going to be 500 tokens and just get all 500 at once. You're doing something akin to 500 passes. At the very end of this tutorial, we'll see some other tricks that people use, but the general gist applies. So that's important for just understanding that to compute optimize, we do this pre-fill stage where we do all the prompt at once. It's not mathematically necessary. It's just obviously much more efficient since you know all of them. And you don't need any of the next token predictions. You can throw those away. So that's why we do it in 2 stages. Okay, so then it goes through a little more details this, and we talked about the fact that there's this KV cache. And so I created a very quick diagram. I wanted to just show this. Uh, so, so this is a form of diagram. You'll see different variations of this in papers and blogs or whatever. But so let's say we have a prompt and it's 16 tokens long and we've numbered them 0 through 15. We're going to calculate a key for each token. So if the prompt is the boy threw the ball, blah 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 blah, the 0th word is the first word is boy. So we're going to calculate a key for boy. We're also going to calculate query vectors for each of these. So we're going to calculate the query for boy. And this causal mask attention says that when you're doing the query for boy, it can attend to itself or it can attend to any of the earlier words. In this case, there's only one earlier word, the 0th word. So these two are all that it can see. By the time you get to the very last token number 15, then it has itself and the 15 tokens that all came before it. And so your attention scores, you're going to have 16 of them, and they're going to sum up to 1. One of the things that I want to point out here is whatever, the end of this prompt is, whatever. What is the boy's name? Whatever. So you have name, and the query here for name, this exact same vector is going to get used to be dotted against all of the different keys. So name is going to get dotted against name's key here, and name's going to get dotted against boys, the, is, what, and so on and so forth. And so this very same query is going to get dotted against each of these. And then again, it goes into that calculation with the softmax and the normalization, and they sum up to 1. I think most people find that pretty intuitive. What's not as obvious until you actually sit down and think about it is that any particular key, so let's just say this key for the very first token, it's the exact same key getting reused over and over again, whether it was in the attention for the first query, the 0th query, or the next query, or the last one. So this same exact numerical vector, let's say it's, whatever, 128 floating point numbers, has been used 16 times over and over again. So so that's an important concept, and that's the reason why we're able to cache these keys. Now, the same thing is true for values as keys. We are able to cache them because they never change. Depending on your positional embedding, you may need to know that. But once you know basically what the token is and what the positional information is, then every number in a column as shown on this diagram is this, or vector, is exactly the same. It's also true that all the queries in any given row are exactly the same. All right, everybody with us on that? Because we're going to talk about strategies for optimizing, speeding things up. And so you really need to know that like the queries are identical across a row, not this way, and the keys are identical vertically, but not across. So we'll come back to that in just a second. But so then what we can do is we can cache keys, and I'll show another diagram in a second that makes it like even clearer. So we talk about the memory requirement, and KV caches can actually get quite big. So I forget the numbers here, but basically if you have a context that's 10,000, then you're going to have 10,000 of them, and you're also going to have 10,000 for every layer. So if your LLM is 48 layers, so that's 480,000 keys and 480,000 values that you're saving off. I will say, however, though, attention itself also requires a lot of memory, so you really are better off keeping the keys in a cache rather than doing the expensive matrix multiply, all that, all those other calculations. That's just going to be even worse. So, but so that's one of the things that we'll be looking at is this trade-off around the memory requirement. All right, keeping on going. So then we talked a little bit about hardware accelerators, and basically we said that, hey, they support lots of data types, and they're going to have, good like matrix multiply, matrix vector multiply, vector multiply, all these kinds of things. And they're going to be able to do a lot of it in parallel, sort of SIMD style. Okay, so a few metrics that we can talk about. So time to fill first token, or time to first token latency. So that's a user types a prompt, hits enter, how long until they see the first output from the LLM. The intertoken latency is just how quickly is it spitting out subsequent tokens after that. Two more metrics. There's three more. End-to-end latency. So that's the time from when they hit enter until they get the complete final output. Okay. Oh no, sorry, only two more. And then request wait or queries per second. This is something that if you're the guy who owns the server, you kind of care in terms of how many customer requests can my server and GPU handle. And you sort of care in the reverse if you're a user and you're like, hey, you know what? I have this data set of like a million things and I want to run them all through the LLM. You want to know how long is it going to take me to run all million of them through the LLM. So these are all things that we might measure, and also certain techniques might possibly have a trade-off where you say, I improved the end-to-end latency, but it actually increased the time to first token, something like that, right? Or vice versa. I reduced one, but there. Question in the chat. What happens if you're short on memory? Does it crash? Does it still perform the math operation, but slower? So there's different ways that you can implement things. If you naively implement attention and you just say, hey, do this big giant query calculation and key calculation and then multiply them together. If you run out of memory, then basically, as far as I know, like PyTorch, all the frameworks, you get an error and you're just screwed. You're dead. There's no, maybe you can try to, I don't know, put things in some sort of try-catch block, but generally speaking, you're pretty dead in the water. Um, so yes, so one of the things that you'll see in uh, systems is that they're actually actively managing the memory. So we'll talk about some of these techniques. It's a cool question. Thanks. All right, so then in this talk, in this tutorial, there's model architecture choices, there's system optimizations, model compressions, algorithmic optimization. So we talked about some of the basic architecture issues, and today it's the system optimizations, but this is the beefiest section. So like I was saying, I think before we started the recording, my guess is if with questions and things like that, we're probably going to only make it like 2/3 the way. And then I think the last two sections are short enough that we'll likely finish. Even if we don't finish system optimizations, we can probably finish that and get the rest of it done next week. All right. So we talked about, okay, you can calculate things, how many matrix multiplies are required to do blah, 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 blah. And you see that you get this thing where it's L squared D, where L is the length of your context, and D is the model dimension, hidden dimension of your transform of the residual stream. So you have a term that's L squared D and a term that's LD squared. So if you make your model really big, this D squared term is going to blow up. And if you try to do 128,000, you try to do 1 million, this L squared really, really blows up. So very briefly, we talked about, hey, instead of having one query and one key for everything, maybe you can just have one query and reuse that. Turns out that doesn't work very well. That's too aggressive. So in the middle, you have grouped query, and that actually works reasonably well. So this diagram, if you look at it physically, there's half as many queries as if you did one for every token. Realistically, you're probably reducing it a little more than that, maybe like one for every four or whatever. But so basically, if you did one for every 4 tokens, then you would be cutting the calculation down by a factor of 4 and getting very similar performance. So there are some LLMs out there that use group query attention. Another thing is on the MLP side of the transformer, you can do a mixture of experts. And so then Mixtral being the most famous MOE model, although for all we know, GPT-4 is probably an MOE model. So Mixtral, it's 8 experts. They use 2 at any given time. And so you have however many parameters allocated to the MLPs, but on any given pass, you're only using a quarter of those. You're only using 2 out of 8 for every layer. And this technique, I think Mixtral's been pretty successful with Mixture of Experts. So that's just very, very quick on those architectural changes. So now we get to today's section, the system level optimizations. And so this is some really clever engineering stuff that people have done in here. So very briefly, here's a diagram to recap those metrics we talked about, okay? So you put in a prompt, and let's say your prompt is really long because you say, hey, LLM, please read my resume that's 3 pages long, and then give me recommendations for how I can improve the wording on things. So if that's, a couple thousand tokens, then you can, in one fell swoop, say, I'm going to compute attention on all 1,000 of these tokens. And in particular, when I compute the attention, I'm not going to throw away everything. I'm going to save all the numbers for the keys and the values. Okay. And then at the very end, I think, what did I say? 5,000 tokens? The 5,000th token is going to predict the next token, the 5,001st. That's the first token of its response. So the time to do this red box, that's the time to first token. Then you do one token at a time, dump, 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 and that's your inter-token time. End to end is when you sum up however many tokens it spits out another 1,000. So then you have 1,000 of these times. So that's your total end to end. And throughput is just sort of the idea of how much of this can you squeeze through. Plus, you may have multiple users. This may not be the only user on your server. So your overall throughput is just however many and how fast can you squeeze all of this out. All right. So if we get through everything, what we're going to talk about is optimizing the forward computation, making the device, I'll say GPU, although it could be a TPU, it could be Amazon's special, whatever they call Inferentia hardware, or anybody else's, special hardware, Jetson, whatever you name it. And then another subsection on leveraging the LLM inference characteristics. Okay, so not going to go into super mathy details, but in terms of the forward computation, there are things that we can do. We want to finish this forward computation as fast as possible. And so we're going to see a couple slides here on 3 techniques: flash attention, flash decoding, and distributed inference. Okay, all of these are going to do the exact attention mathematical calculation, but they're going to do it differently. Flash attention, I'm guessing probably most people have heard of it. This is the diagram from the paper. I think this is the only slide on this. No, they got a couple more. But basically, the main gist of flash attention is this idea that if you do the vanilla calculation as written, okay, you dot your Q's and your K's, if you can see my mouse. You have a scaling factor. Then you're going to run softmax, and then you're going to take this result, which is a bunch of numbers that add up to 1, and you're going to multiply it by the values that you've already computed from your input tokens. If you do this very naively, then you're going to have an intermediate value S, which is the result of multiplying the Q and the K matrices. Okay. And so literally, if you're using the matrix multiply, I don't know what it's called, but command on the GPU, then what that GPU is going to do is it's going to read the Q and the K matrices from high bandwidth memory into SRAM, get it into the cores, do all the matrix multiplies, and then it's going to write this value S out to high bandwidth memory. Then when you try to do this softmax and scaling, it's going to read this S that you just wrote to memory back. And then it's going to do the calculation and write a new intermediate value P. And then if you do O as a separate operation, it's literally going to read from memory the same thing you just wrote a moment ago. And it's going to read the values that you computed a little while ago. It's going to do the matrix multiply thing. And it's going to write that result out back to high bandwidth memory. So clearly, if nothing else, you could just say, well, I'm not going to bother doing these writes and reads. I'm just going to do this calculation, and then, do the next thing or whatever, right? Um, but the problem is, once you get really big, you cannot fit all of the Q and the K in GPU memory at once. And therefore, you can't have it all sitting in memory and then do this softmax calculation and have that sitting in memory and then. So what they do fundamentally in flash attention is they figure out a way to break the Q and the K matrices into smaller tiles and try to do as much of S, P, and O, like we just talked about, all together without having to do the write and then the read again. And then eventually it's going to require a little overhead to stitch things back together. And at one point, I don't remember exactly, but at one like very key point, uh, there is explicitly a calculation that flash attention does. And if you look at it, you say, wait a second, it's the exact same calculation. It does it two different places. And it's because it's actually faster for a GPU if it has the two matrices in SRAM. It's faster to multiply those two together than to read the result that's sitting there waiting for you in high bandwidth memory. That actually the floating point math is so freaking fast that it's faster to do math than it is to read from. And again, this high bandwidth memory, this is the expensive fast memory that we have on GPUs, but it's still compared to, the stuff on the chip, it's still slow. Um, so so bottom line, flash attention, what it's doing is it's tiling the operations so that it can, as much as possible, make all of this SP&O all one atomic step. And it does also use some tricks of recomputation because it turns out that that's faster than reading from memory. So when you combine those two together, then you get a pretty decent speed up. And this works well in the pre-fill stage where you have many, many tokens all at once. When you get to the decoding stage, however, you only have, if you're caching the keys and values, you only have one brand new token that you need to calculate both the queries and the keys and the values. And so this whole idea of tiling, you don't need to tile something when you only have one. It's tiny. So it turns out that you only use flash attention in the pre-fill stage. You do not use it in the token by token decoding stage. Any questions, comments? Any other people who've used flash attention more? Anything I messed up or important I didn't hit?
And of course, this is inference focused, but flash attention. Flash attention is used heavily in training.
Yes. So it's used in training, and it's used when we're talking about inference, it's used in the pre-fill part, but not the decoding part. Yep. Perfect. Okay. Um, so here's a slide I don't know. Well, okay. Basically, what they're trying to show is the thing that I just said verbally, is that when you do decoding, you only have this dark blue. You only have one brand new query. So the calculation that you need to do is much, much smaller than what you need to do when you're feeding it a whole bunch, thousands of tokens of new tokens all at once. Okay. So if you do clever KV caching, you really only need to do this little bit, and it turns out that flash attention doesn't help you. If you literally, I saw this somewhere, if you literally force a GPU to do flash attention during this phase, it'll actually run slower than if you do vanilla, naive, not flash attention. So flash attention is not a good idea for because there's again you're tiling, there's like whatever. So so we need some other trick for speeding it up. So there's this idea of flash decoding, and the idea here is that I'm trying to remember this diagram here. Uh, um, Right. So I have one brand new query, okay? But let's say again that my prompt was fairly long. It was 5,000 tokens and it was like my whole resume. And now it's starting to spit out words and say, "Oh, your resume looks pretty good, but I would recommend a few changes. Number one, this, number two, that, blah, blah." It's starting to spit all that out. Um, so for the 5,001st token, it needs to calculate the dot product of that query with all 5,000 keys that came before it. There's really no reason why you have to do them in some sort of sequential order. So what you see here is you could split those 5,000 keys into 5 chunks of each 1,000. And you could, in parallel, say, dot the query with the first fifth, dot the query with the second fifth, dot the query with the third fifth. And the dot products that you get, q dot k, are all going to be exactly the same as if you did it in one big thing. What is going to be a little bit more costly is that there's this scaling that you do. And so that's going to actually require that you do a reduce operation. So what they do in flash decoding is they do the running sum of just this fifth. And then there's a running sum here and the running sum there, running sum there, running sum there. Then you have to take these 5 parts and you have to reduce them into one grand total sum so that you know what to divide by, what to scale the whole thing by. Uh, but so this is a relatively straightforward optimization. But again, if you just didn't think about it and you just vanilla said, uh, um, do this particular operation, what you might do is the CUDA kernel might say, "Oh, I'm going to do the matrix multiply in chunks." That it probably would figure out, but it wouldn't necessarily figure out that while that chunk is there, you can calculate a intermediate running sum, and you can save that off, and then you can just reduce total up all those running sums. So if you did a vanilla thing, I think what would happen is you would do this part in tiling, in chunks, and whatever, but then it would go back and make a second pass and calculate the sum of all of these from scratch. But you already had it in memory, so you really didn't need to do that. You could have just very quickly done this. And so I think that's the main innovation of flash decoding, is keeping around these running subtotals. I see some stuff on CUDA in the chat. If there's anything you guys want me to respond to, please let me know. But otherwise, feel free to use the chat. And I do try after it's over to catch up and see what I can learn from you guys. But if there's a question I'm not answering, please let me know. Okay, so that's 2 techniques. A flash attention, great for training, great for prefill. Flash decoding works for inference one at a time when you only have one new query. And then a couple other things in general you can do. You can split things up and do more parallelism. Okay. Um, so tensor parallelism, you can just break up when you have large enough matrices, you can just break them up and you can split them across multiple servers, multiple GPUs, whatever. It's really, really easy when you have multi-headed attention. So if you have like 8-headed attention, all the heads are independent. You can easily split that sucker over 8 different servers, 8 different GPUs. There's ways that you can actually do it even you could split it more than that. You could split it 16, but then you do need a little bit of communication between them. You can do sort of this pipeline parallelism. I don't know exactly what they're referring to here, but like if your LM has 48 layers, then theoretically you could be doing a certain something on layer 1, and then you could pass off onto somebody else to do layer 2, and and so on and so forth. So you're sort of optimizing in terms of like where your model weights are, not having to constantly load new weights or whatever. If the whole model doesn't fit in memory, you just break things up. And so there's a lot of ways. I think most of these are pretty intuitive. Actually writing the code, getting it to be debugged, get it to run fast, all that's something else. But if you look at VLLM or some of these other tools, it's pretty straightforward, the notion that if you have a very big model, we can spread this computation out if you have enough hardware. And sometimes you just flat out have to, because a 405 billion model, I don't care if you have 48 gigs of RAM on your GPU, that doesn't it's not all going to fit there, not by a long, long, long shot. And then we'll talk about some more techniques specifically around this, but there's this idea that if you know you're doing the pre-fill part where you've gotten 5,000 tokens all at once, and you know that you're doing decoding where you're doing one token at a time, you can be clever about deciding which server, where do I want to send these various things so that they work well together. I think this is just talking about having a machine dedicated to prefill, a machine dedicated to decode, and then you can kind of optimize the way those machines are configured. But I'm not 100% sure exactly. But the idea, I think, is fairly intuitive what they're talking about. All right, and I think this wraps up their slides on these three things. Yeah. So, any questions on this first section, which covered flash tension, flash decode, and various forms of distributed inference? Okay. So now this is the gnarliest section. This is my favorite part of the tutorial. So, we want to take our expensive GPU and we want as much as possible to have 100% utilization of that GPU. And it turns out that if you just very naively implement a transformer and you run things through, you're going to have holes. There are going to be places where uh, two things are going to happen. There's going to be places where your GPU is not really 100% fully utilized. Okay. During decoding, it is going to be very difficult for you to 100% utilize it because, again, you're only getting this one query. And so you're doing this matrix multiply of a very tiny matrix by a bunch of other things. It's just you're not going to get 100% utilization. The other problem you're going to have is if you batch users, okay, and I pass in a prompt that says, what is the capital of France? And it's like 10 tokens. And the response is going to be, less than 10 tokens. Okay. And you stick me in the same batch as somebody else who pastes, the first 500 pages of War and Peace and asks some question about the main character, right? The GPU is going to be chunking on and on and on these 100,000 tokens for the first 500 pages of War and Peace. Meanwhile, basically, it's going to be all zeros, all padding for my 10 token question. So we're going to have both of those kinds of inefficiencies in the system that people want to address. Okay, so the first idea is continuous batching. So naively, when we do training, this is one of the things that we do, is we say, I've got 4 different users here in the rows, okay? User 1 has a 3 token prompt, and then we're going to start answering and do decoding in the blue, okay? And then this user has a shorter one, this one's got 3, and user 4 has a longer one. And so if you look to the right, these are, hypothetical answers, but these are fairly short answers. But what you can see here is that user 2 ended up having the longest response. And so it took 8 tokens in order to finish answering. So if we do just a very naive, simple 4-person batch, what would happen is we would start processing the decoding here. And then by the time that, say, user 3 finished, we're still processing. We're still processing. And it's only when we get to the very end of user 2, now we're basically ready to start a brand new 4-person batch. on users 5, 6, 7, and 8. This would be a super straightforward. If I just wrote this in PyTorch, this is exactly how I would write it. I would basically say, grab 4 prompts, put them in a 4 by whatever tensor, run inference. When it's done, grab the next 4 prompts. Okay. But so that creates these white holes where you're not doing anything because those users already finished. So the clever thing you can do with continuous batching is you say, oh, well, user 3 finished. Let's just start putting in the tokens for another user right then and there. And there's no need for you to wait. But it just means that you need to be paying attention. So you can't just run all this to completion and then look. You have to look after every token to see whether or not somebody's finished. And then, and then of course, there's like a lot of bookkeeping you need to do to say, well, I started, right? Instead of starting everybody at position 1, now you got to keep track of, I started this person at position 6 and blah, 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 blah. And I think there's another slide. Yeah. So you end up having to have these weird masks that you create in order to make sure that the attention for each user only uses, you just get that nice triangular thing that I showed when everybody starts at position 1. But you're gonna have like weirder things like this when you do this. But it's not that much bookkeeping. It can be done, and also this bookkeeping can all happen on the CPU. While your GPU is going and crunching and crunching and crunching. So I think for the most part, this computation can all be done more or less for free. Some of the masks you have to do on the GPU, but most of the computation, the bookkeeping, can be done on the CPU in parallel.
Hey, Ted.
Yeah.
Yeah, quick question if you can go back one slide. So it looks to me like you can use flash attention for the prefill on the first 4 queries, but you don't get that performance advantage for these other batched queries. Is that right? Because you're out later in your diagram, your matrix, you're generating 1 token at a time.
Yeah. I don't know exactly how people do it. Ultimately, what you're going to see in the advanced systems is that when we say S1, we're not really talking about 1 token. We're talking about doing prefill of 1 chunk that's going to be commensurate with 1 decoding. Does that make
I
sense?
I also presume that in the context of SIMD system, each GPU, like each row, or each batch entry, may potentially be operating on a separate GPU, and it could potentially be optimized to focus on flash attention versus decoding,
Yeah.
prefill versus
You could,
decoding.
yes, Dave, you could definitely do that. But this is talking about like if you have a batch on 1 device, the naive thing you would do is if you say, oh, I have enough memory on my GPU, I'm going to serve 4 users at once. The naive thing you would do is you would just build a 4 by whatever, input, and you would run it all to completion. And so this is saying that if you don't do that, if you don't run it to completion, but rather you sort of inspect at each step. But so Roger, for your question, think of T1, 2, 3, 4 not as token 1, token 2, token 3, but time slot 1, time slot 2, time slot 3. So I'm going to do a chunk of pre-filling, and then these are literally 1 token at a time. Does that make sense?
Not sure I follow, but that's okay. I'll take it
Yeah,
offline.
I don't follow. Am I on mute? No, yeah, I don't follow that one. So I think the only way I can think it can potentially be accomplished is even on a single device, there are multiple cores, right? And essentially are broadcasting the instructions to all the cores, but the way you are distributing the batch is that for, even though it is not single instruction then. So maybe you're doing some partitioning of your cores so that some cores can attend to some part of the batch, which may potentially do flash attention, and some may be focused only on decoding.
Yeah, I'm not sure about flash attention versus decoding. That's a good question. The attention calculation is identical whether you're doing the yellow, the prefill, or the blue, the decoding. But how do you split that out? Yeah, I guess what would happen is you really wouldn't then have a batch of size 4. You would, um, I think you guys are right. You'd have to put all the yellows together in one batch and all the blues at any particular time step, all the blues together in a separate batch, um, and send them separately to the GPU. So it would not be a literal. So this is more of just a conceptual set of 4 users all being handled. But yeah, you're right. You can't really do it as just one literal 4 by whatever tensor input. Did that make more sense for your question, Roger?
Well, actually, now I'm kind of understanding the time concept. Basically, you're doing a batch of 4 over and over and over because that's what you do with inference. But if start feeding in the next sequence into that slot.
Yes, that part I hope makes sense. That at time step 7, instead of doing work for 2 people and nothing else, you start feeding in 2 new people.
Right. It
That
just means
part.
that you can't. Yeah, you just won't be able to leverage in any case. You won't be able to leverage the flash attention.
Right. So the thing that I have not been able to answer, because I don't live and breathe this stuff, is exactly how do you manage optimizing the yellow ones with flash attention and the blue ones with fast decoding when you're trying to do them at the same time. Yeah.
Right.
But I think, and there is another set of techniques coming up that will somewhat better address how you mix and match yellows and blues, but it still doesn't address, like, fundamentally at the code level, how do you do that? But I'm thinking that basically it just means that you're probably just issuing the commands separately, because I don't know if you know, like, GPUs don't operate lockstep with your CPU, right? They have sort of their own queue of work to be done. So you can just sort of like give the GPU a bunch of stuff to do. So you could say, here's a bunch of flash attention things to do. Here's a bunch of flash decoding things to do. And they'll pile up until it can, right. And when you're lucky, you get 100% utilization is when you can actually fast enough pile up all the things it needs to do. So I think in this case, where you have separate users, you could just issue them separately, but let them pile up and let the GPU do it as fast as it possibly can.
So Ted, as you were going through this and talking about using the multiple users and the I don't remember what you call it. Is it continuous batching?
Yeah.
I was multitasking while you're doing that, and it made me think. Whenever I see this disconnection between memory space, compute space, and users, I think security, right? Like that's the very first thing that jumps to my mind is as soon as you disconnect, especially just very simply like memory and compute, as soon as you disconnect those two, you have an opportunity to have something switch in the middle. And I just put in chat. It's funny, like while you were doing that, like that's the first thing jumps to my mind. So I started searching for, has anybody hacked an LLM? And it looks like there are ways to inject things in here. And so if you have a shared memory, you would actually be able to inject into other people's memory as well, which is just again, one of the things to think about. Everyone who's kind of listening to this is just, I thought it was an interesting point to raise that as we're thinking about optimizing and disconnecting those things, one of the holdbacks always is now we have to add an entire layer of security. So the gains also have to be significant enough to compensate for the complexity and compute time required to compensate for the security layers. So sorry, just this one especially though, I was like, oh my God, multiple users' data sitting right next to each other using the same compute resources. I know what to do with that. And sure enough, there you go.
No, that's great. Yeah, I saw. I think it was a different reference. I saw a paper where they demonstrated, like, to nobody's surprise, that if they had access to the hardware, they were able to read uninitialized GPU memory and find old data from people.
Oh yeah, of course, because they
right?
don't zero it out between
No,
operations. Like you
no,
can't do
right.
that. That's
So
too expensive.
that was like, oh yeah, that would be bad, and at least nominally you don't expect the bad guys to have access to the GPU if they're just a user.
What this other guy's kind of figured out is how to embed key value pairs that were not part of the source data, that have semantic meaning beyond what was intended. So you essentially embed, I think he said, like, the person's 102 years old and lives in the matrix into an image. So you actually embed that into the binary in a form. Anyway, so we're off to the side, but like, again, as soon as I saw this graphic, having seen this before in other operations, shared early web servers had to use lots of shared memory, and that's where the number one hack is if you could do memory injection, and then you'd be able to cross threads, and those threads would then impact other users. So anyway, just old school.
All right. So any more questions? So we may not have 100% explained exactly how it works under the hood, but the general idea for continuous batching is, when one user finishes, don't wait for all users to finish. Immediately start another user as soon as one user finishes. Okay. So here's another topic, which is your KV cache management. So let's say that you pre-allocate the maximum sequence length. So let's start with something small, 32,000, okay? And then, you have my query over here, which is, what's the capital of France? I mean, you just wasted all of this memory, when, you know, you didn't actually need it, right? So, oops. So pretty intuitive thing you could do is you can break up, your memory into pages, just like the way computers break things up into pages, and basically this is a virtual memory scheme, uh, for your KV caches. So now it does mean that these things are no longer contiguous in memory. There could be some impacts of that, you got to manage. But overall, because you can have a mix of very short and very long prompts, I'm pretty sure that, like, this is in general like a win for everybody. All right. And then we've got a bunch of slides here where they basically show, like, how you have to, like, have the physical block, and then you have to have some, like, pointer to it, whatever. I didn't pay too close attention to this set of slides. But again, it's just showing that the physical memory and the logical do not necessarily match up at all. Okay, so then one of the most important topics is chunked prefill. And so this particular slide here shows you sort of the end result, but I'm going to flip back to my diagram earlier to kind of break it down a little more step by step. Okay, so we have here our 16 tokens, and everybody agrees this is the blue part is the valid attention mask, and the whatever light yellow, it's all zeros. Okay, so now, would you all agree that if instead of doing that in one large step, I did just step one, which is this top quarter, And then step 2, I calculated this quarter. Step 3, I calculated this quarter. Step 4, and then I just concatenated these results, these vectors. Is there anybody who has any concern that this is not mathematically exactly the same as if I do a 16 by 16 matrix multiply? Instead, I just do 4 separate 4 by 16 matrix multiplies. Any questions, any concerns? Okay, so now if you are okay with that, this is the exact same mathematical result, then are you okay with that? I actually don't need to do those big yellow sections since I know I'm going to end up with all zeros at the end. So between these two, I can just do a 4 by 4 and a 4 by 8 and a 4 by 12 and a 4 by 16. I don't actually have to do 4 by 16s. I can actually, if I want to, do some smaller ones and then do some bigger ones at the end.
And each step, you're doing the caching, right?
So at this point, I'm not talking about, that's the next step. I haven't done any caching. I'm just simply saying that I could take my keys, the first 4 keys and the first 4 queries, and I can compute these blue squares. And I could take the first 8 keys and I could take the next 4 queries and I could calculate this set of blue squares. And this is absolutely 100% identical mathematically as if I had just done a large 16 by 16 matrix multiply. Okay. All right. So now we've done 2 steps where we've simplified this overall thing into a series of we're going to call these chunks, right? Where we've broken up the query into smaller chunks. And now what I'm going to say is, remember before I purposefully emphasized that the every single one of these 16 blue squares for position 0 is the exact same vector. Okay, and every single one of these 14 is the same, and every single one of these, however many, 11, is the exact same vector. So there's really no need for us to calculate this thing 16 times. So what I could do is, now that I'm talking about steps, if I complete this step, I have the keys and values for position 0, 1, 2, and 3. I could save these in memory. I could save them in some type of cache. And then when I get to step 2, I don't need to calculate these all over again. So with KV caching, what we do is in the light blue, we say we're going to reuse the numbers that we already figured out in the previous steps. And so this is the pattern for chunked prefill, where you break it up into smaller chunks, and then the output from one chunk becomes the cached part for the next chunk. Now, again, if we're looking at, say, this particular row 7 here, this query does need to get dotted with all 8 of these keys. It's just that 4 of the keys come from a cache, and they're very fast. And these 4 have to be computed by doing matrix multiplies, and so they take a little bit longer before they're ready. But once they're all ready, once all 8 are ready, then I just do a regular matrix multiply of this particular query with these guys here. Any questions? Does that make sense, chunked prefill?
Yes, I'm wondering why can't we also do the same during training as well? It will be also more efficient. Why is it only at the inference stage? Do I make sense or no?
Why? I think the reason is because matrix multiply is so fast that it actually is quite efficient and fast to just do the 16 by 16 matrix multiply. Okay. The reason you use the KV cache is because actually, when I get to the very end, we're going to predict, we have token 15, we're going to predict token 16. I cannot do anything about it yet, but once I have token 16, I'm going to have another row down here. I'm going to have a new query for token 16. And I'm going to have all of these keys that I'm going to need to reuse in that next step. And because it's I don't know how to describe it, a physically next step that I cannot do now, I have to wait until I do my next token prediction. And remember, like in real LLMs, it's not just me computing these 16 things and now I know what the next token is. No, the output from this is going to go into the MLP layer, and then I may have 47 more layers in my LLM, and they may be all distributed on different servers, and whatever. And then we're going to get, let's say the vocabulary size is 30,000. We're going to get 30,000 probabilities that all sum to 1. And if we're not doing zero temperature, we're going to do sampling from this and get a random token from it. And it's only after all of that happens that I know what the 16th token is. And then I can append it here, and then I can start this process again. So because of all of that waiting time, I can't just do a matrix multiply now. I have to just sort of save my keys and values and keep them lying around. But the reality is, if somehow magically you did tell me I know what tokens 16 through 20 are, instead of doing KV caching, I think you're better off just doing a whole bunch more matrix multiplies, because once you have them, the you know, those matrix multiply cores, right? Whatever they talk about, how many tensor cores are in your GPU, whatever, that you know, they scream and they do all of it. Not 1,000% sure of that answer, but does that seem intuitive? Does that sound like that's the right answer?
I think
Thank you. I think I also need to familiarize myself more with how they train these large models and optimize them during training. It's definitely different than the inference stage for sure.
Yeah, yeah. If like somehow if you knew that the answer was only going to be one token, it was just going to be yes or no, whatever, then I think, yeah, you would treat it more like training. You wouldn't have this KV cache business. You would just sort of blam. There is another factor. Sorry, Dave, I know that you were about to say something. Also, the amount of memory that you use, where am I? When you do this all at once, is quite large. And if you break it up into chunks like this, you're basically dividing the amount of memory in, if it's 4 steps, in 1/4. And we don't really have this concept of memory times time, okay? But you're not getting a free lunch, because you basically need a quarter of the memory for 4 times as much time. But we don't really care about time when it comes to GPU memory. We care more about just total at any one given time. So breaking up this calculation into chunks actually is a little easier to manage, because now you have these smaller chunks, and again, if you're doing the bookkeeping, you can decide how many chunks can I afford to do, and which server do I want to do this chunk on, and blah 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 blah. You know, you can do a lot of that kind of stuff. You can't, if you just have this one chunk and it's like I need 95% of your GPU memory, then there's no flexibility. You just have to say, okay, everybody else stop. We're just going to do this one thing right now, and when it's done, then we can resume with other stuff. When you have smaller chunks, you can actually kind of.
Hey, Ted.
Yeah.
When you're doing this, it looks like Yeah, it looks like it's actually at this level, it's a block diagonal, so it's less than 1/4. It's like 1/16 of the
This
memory
is
that's being required,
1/4.
right?
This is 1/4, right? In terms of the
Right.
queries times the keys. But then this one
But
is
the
a little
matrix
less than a
multiply is
quarter.
just the,
Are you still there, Roger?
okay.
You're right. So it turns out that
Yeah,
the
I
last
don't have a
one
great,
is only 1/4, and these are actually even a little cheaper. Right? If you did this version of it, it would all be 1/4. But when you simplify it, then you're actually, to your point, gaining even more. Yep. And one of the techniques we're going to see later specifically says, if I had the choice of recalculating key 12 or key, wait, how's it go? I don't remember, but basically if I have to redo this calculation, it's cheaper than if I have to redo this calculation. We'll get to it.
yeah.
But you're exactly right. So in fact, it isn't just repeating 4 things that are each 1/4 as expensive. You get an even extra boost. And theoretically, the more chunks you have, the more of a boost you get.
If you look at the causal mask portion of it, the light blue stuff in the next slide, the next one, is coming from KB cache. That's not in the causal mask, right?
This is in the causal mask,
So the
but it's
causal
just a
mask is
region
just the
that's all
4x4.
ones. Sorry, what did you say?
Okay.
So this region that's now light blue, it's all ones, and this region up here that was all zeros, I removed. Right, so we go all the way to the beginning here, right? I mean, there are chunks in here that are 4x4, just they're all ones. And then these are all zeros. Sorry, I didn't hear if you said, I see you're muted again, but I didn't know if that answered your question.
Yeah, that's good. I have a bad internet connection, so
Sorry.
I'll be quiet here.
Yeah, I can hear your audio dropping in and out a little bit. Okay. All right. Well, hopefully this helps because chunked prefill is a cool concept, but we need to talk about basic chunked prefill before we get into crazy advanced chunked prefill. All right, so going back to their slides, imagine that you did some very naive continuous batching that we were talking about on the previous slide. Okay. And so imagine that you have user 1 and we're decoding some stuff and it says the capital of France is the city called Paris. And then user 2 comes along and we say that we're going to do some prefill for this person. And it's the first 500 pages of War and Peace. And so basically, once we commit to doing that, we can't really serve any other users once we've sort of queued up this massive set of calculations on the GPU, right? So one of the other things that's beneficial about chunked prefill, this idea where, on my diagram where I broke it up into 4 chunks, is after each chunk, you can decide how expensive is that next chunk and how many other users can I also serve in parallel at the same time as this chunk. And so if you're doing that and you're being clever about it, then you kind of have this idea that even while you're doing 2 chunks here, 3 chunks here, 2 chunks here for different users. And remember, these chunks, this was something that came up before. These chunks are not one token. I mean, I wrote it as 4, which is pretty small, but they're probably, I don't know, 8,000 or something, you know, some really decent sized chunk. So, so these green squares on the right for chunk prefill do not reflect one token, but rather sort of one time slice worth of prefill activity, and the blue is one time slice worth of decode activity. So yeah, so that's chunk prefill, and chunk prefill is very cool. So chunk prefill lowers your memory requirement, but possibly it means that you're doing a bunch of KB cache accesses and stuff like that. Here's this diagram that basically, I don't know if this diagram really communicates this, but what they're trying to say here, the y-axis here, the vertical axis, is how much can you utilize your GPU during doing this arithmetic intensity. So basically, how much can you keep your GPU utilized, essentially doing matrix multiplies. They say arithmetic intensity, but for all purposes, yeah, we're just talking about matrix multiplies. Okay. And so what they're saying is that the prefill portion, if you give it really big chunks, you know, whatever, 8,000 by 8,000, whatever, you can really keep your GPU very highly utilized doing matrix multiplies. Decoding, yes, you might have a bunch of keys, but you only have one query and you can't really. But there is a separate issue, which is that if you have a very long context, whether it be prompt or whether it be stuff that the LLM has generated, whatever the grand total is, if you're now on the 100,000th token, you need 100,000 things in your KB cache, and it becomes very memory hogging. So even though it's very low compute, if you had several users that were all asking these 100,000 token questions of the LLM, you can't fit very many of them on a GPU because you're going to run out of memory. Okay. And if you had a lot of prefill activity, you can't fit that many users on a GPU. I mean, technically you can fit them, but they're all just going to wait sequentially. You can't fit them in parallel because you're going to run out of compute. So what they say in the Sarathi paper is the ideal point, you do some math, you figure it out, is to do some mix of prefill and decoding. So in this previous chunked prefill, you see that we're doing a mix of blue and green at any one vertical time slice. And they basically go into the, do we have another slide? No. They go into the gory details of figuring out like exactly how much prefill you should pair with decoding. Oh, by the way, if you guys didn't notice, in almost every single slide in this wonderful AWS presentation has a web page or archive paper link. So, very, very, very cool. So if you have questions or if you're interested in learning more about any of these things, they did a wonderful job. So giving them another high five. So there's a few more details to Sarathi, but the main idea is that they figure out this clever balance between prefill and decoding in order to really maximize, make sure that we're maximizing our GPU. Now, I certainly can imagine that you're also going to run into some circumstances where, let's say, you don't have any prefill left, all you have is decoding. you have no new users, but you're still continuing to generate more tokens for your existing users, I mean, then you're just out of luck. You're just not going to maximize your GPUs fully. Any questions? All right. If you guys are interested, there's this really cool paper I just read called Writing in the Margins. And they figured out that if you're doing this chunked prefill business, that at the same time that you do this prefill of this green block, well, not at the exact same time, but once you've got everything loaded up and you've calculated a bunch of stuff for the KV cache, you can use those keys and values and you can do inference on them. So you can actually like ask a question about the information that's contained in this prefill chunk. And then when you get to this next one, you can say, now let me ask you a question about what's contained here in this prefill. And then you get to the third one, you say, let me ask you a question about what's in here. And then finally, you get to the user's actual prompt and you start doing decoding or whatever. But so what they do is if you have like a RAG workflow with very long chunks, I mean, some RAG you don't, but if you had like really long PDF articles, and so you're pulling back, 6, 10 of these really long articles, what they do is they do summarization questions against each of these little green chunks along the way. And it's actually very cheap because you've already got the keys and values sitting there in the KV cache, fully loaded up. So I thought that was just like super, super, super clever engineering. All right, looking at the time, trying to remember. Okay, I think we can get through just a couple more slides here. This stuff is not as heavy. This is basically just talking about how are you going to manage your KV cache? How do you decide how long you keep stuff in the cache and when do you like get rid of it? So first thing they say is you could do something stateful. So for example, user says hello, LLM says hi. I've now got like hello and hi in my KV cache. But remember, we got to compute those MLPs. We've got to compute 47 more layers. We've got to do all this stuff. And then I got to wait for the user, which is seemingly an eternity for a computer, before they finish typing what's the weather and hit return. So let's say that took all of like 30 seconds. Am I really going to keep this KV cache around for 30 seconds? The answer is actually probably yes. So naively, if you didn't keep it in the KV cache, you would recompute the keys and values for hello and hi as soon as the next turn came around. Instead, what you can do is you can actually just keep them around. So then there's this idea of prefix caching where you don't even have to limit the part you're keeping in the KV cache to that particular user. Any user who starts their question with the same first 16 tokens is going to have the exact same 16 keys and values, even though the rest of their whatever is different. I don't know exactly how this is implemented, but there's the idea that basically you don't even have to say, I'm waiting for user Ted to come back with this next thing. It's just anybody that matches on this prefix, I can go and just yank that out of the cache. So basically you can have the cache be indexed by the string versus being assigned to a particular user or something like that. And you can get even fancier with this to say, well, instead of just like the whole thing, let me organize my KV cache a little bit even fancier. Sorry. And so there's this idea of this radix attention where you basically build a tree of like different conversation turns and longer. I mean, I don't really know how often does somebody ask the same question or start with the same whatever on ChatGPT. They have 1 million users per day, so I guess some of them must repeat. And that's basically the idea in these. There's another one here, this slide before, that's called pensive, and I don't have the exact workings like really down, but basically they've got 3 layers, so you can have KVs cached on your GPU. But if you run out of memory there, then you can use main memory, CPU main memory, as cache. And you can actually run out of memory there. And so they have an algorithm where they have to decide, what am I going to evict from my cache when I run out of room and I need to store something new? And it operates on this principle, which they're trying to show in this diagram here, that yellow is near the beginning and green is near the end. And so what they're going to do is their calculation, they evict, they are more likely to evict something that's near the beginning, because leading tokens require less computation to recompute. And that's this business here, that I would rather recompute this little guy than repeat this bigger guy down here. So that's the thing that I think Roger pointed out. And so that's why their algorithm is not just biased by this or that or age or whatever, but it's also biased by uh, is it earlier? Is it the shorter earlier part of the prompt versus the later part of the prompt? Pretty freaking wild what some people have figured out. So if you put all this stuff together that we talked about so far, flash attention is, again, it does get used in training, but for inference, it's mostly used for the prefill part, and so it reduces time to first token. Flash decoding does that parallelization thing, and so it shortens your inter-token latency by parallelizing that one step. Distributed inference, basically it's just throughput, you're parallelizing things. Continuous batching is a throughput thing because users don't have to wait. You don't have dead time. You just immediately start the next user. Paged KV caching, I guess it helps throughput indirectly. I mean, yeah, it's basically preventing you from running out of memory and forcing people to wait until memory gets freed up. So it will help throughput through better memory utilization. Chunked prefill can actually help multiple things. It's going to help throughput. It's going to help your intertoken latency. And then prefix caching is going to overall reduce your latency, because instead of having to calculate certain attention things a certain percentage of the time, you're like, oh, somebody else already asked that, or you asked that 5 minutes ago. That was, the earlier part of this conversation. And I had enough room, so I kept it lying around in cache. And so I don't have to recompute the attention. And you can imagine, like for chatbot, right? Once you get several turns in, you're hundreds, thousands of tokens in. So yeah, maybe not like 2 sentences in, it might not make that much difference if you had to recompute. But I was just doing something last night, this coding stuff. And so I have big blocks of code, and I've asked now several back and forth questions about it. It's thousands and thousands of tokens. And so I'm sure it's faster to load it from the cache than to recompute the attention on all of those. Do we have another slide? No. So we're at the top of the hour. So we will stop right here, slide 74. Any final questions on all of this good stuff that we talked about today?
Is this like only for their, Trainium stuff, or do they do it for NVIDIA as well?
Oh, all these techniques apply generically. You'll see a bunch of AWS references in here. They're Trainium, Inferentia, whatever. But no, the everything that I've discussed applies regardless of what your hardware is. You still have this fundamental phenomenon that one token at a time is not going to make use of your accelerator's capability to do a bajillion matrix multiplies. And prefill can utilize that. And generally speaking, prefill, it can get high memory, but overall on average is not as high memory. Whereas decoding, you can have these very large KB caches. And so those are the characteristics that we've been talking about, how to marry these different things together.
Great, thanks.
Thanks for the question. Anything else? All right, well, we will see whether or not there's enough time next week to finish this presentation. Let me